In this lesson, we'll be discussing how you can develop and use the properties of integer exponents. Recall that we can write this product 2 times 2 times 2 times 2 times 2 in a shorthand way, 2 to the 5th power. I just count up how many times 2 is written as a factor, and that goes into the exponent. This is considered the base of it. So this is the base of the exponent, and this is the power here. In this lesson, we're going to examine the patterns and learn properties of integer exponents. Using these properties makes operations with the numbers in exponential form more efficient, as you will see here in a second. Okay. So if you look at this table, it shows the powers of 5, powers of 4, and powers of 3. Okay. Our goal here is going to be to use what we know, the patterns that we see in this table, to complete the remaining part of this table here. So we all know, of course, that 5 to the first power is 5 because that's just 5 as a factor once. 5 squared would be 5 times 5, which is of course 25. 5 to the third power would be 5 times 5 times 5, which is 125, so on and so forth. And it's the same for the powers of 4 and 3. Right. If you look for a pattern in the powers of 5, here are the powers of 5, you should see that as the exponent decreases by 1, as it decreases by 1, the value of the power is divided by 5 each and every time. So for example, notice that when we decrease this power here by 1, so we go from the 5 to the power of 4 to 5 to the power of 3, I just take this number here and divide by 5. The pattern continues. When I decrease this power by 1, when I decrease this exponent, by 1, you'll see that this number just gets divided by 5. Same thing here. When this exponent is decreased by 1, the entire power itself is just divided by 5. 25 divided by 5 is 5. Okay. Same thing with the powers of 4. If we decrease the exponent by 1, each time we decrease the exponent by 1, we divide the power by 4. 16 divided by 4 is 4. With these patterns in mind, let's complete the table for the values of 5 to the power 0, 5 to the power negative 1, and 5 to the power negative 2, so these boxes here. So continuing our pattern, notice that each time we decrease the exponent by 1, we divide the power by 5. So continuing that pattern, if I decrease the power the exponent once again by 1, I should divide by 5. So 5 divided by 5 is 1. Continuing in this way, decreasing the exponent again, 0 minus 1 to get negative 1, I'm going to divide once again by 5. So 1 divided by 5 is 1/5. And continuing in this way, once again decreasing my exponent by 1, I divide the entire power by 5, so I get 1 divided by 25. Next, we're going to complete the table for the values of 4 to the power 0, 4 to the power negative 1, and 4 to the power negative 2 using the exact same reasoning. So if you notice, when I decrease the exponent by 1, I divide the entire power by 4. Okay, so 16 divided by 4 is 4. Decreasing once again by the exponent by 1, I take 4 divided by 4, which is 1. Dividing this by 4, I get 1 over 4. Dividing this by 4, I get 1 over 16. Now we can complete the entire table, doing the exact same thing for the values of 3 to the power 0, 3 to the power negative 1, and 3 to the power negative 2. Just divide this by 3 to get 1. Dividing this by 3, get 1/3. Dividing that by 3, I get 1/9. What we can do now is use our patterns that we saw in the table to make a general rule for any number to the power 0 and any number to a negative power, to a negative exponent. What we say is, in general, if you notice, any number raised to the power 0, no matter what it is 1. Okay, so we're just going to adopt that as our rule. Any number that you raise to the power 0 is going to be 1. And if you notice here, any number raised to a negative power is just 1 over that same number raised to the positive version of that power. For example, 5 to the power negative 1 is just 1 over 5 to the power 1. 5 to the power negative 2 is just 1 over 5 squared. 5 squared is 25. 4 to the power negative 1 is just 1 over 4 to the power 1, which is just 4. 4 to the power negative 2 is 1 over 4 squared, and remember that 4 squared is 16, and so on and so forth. So you can see how this general rule is used. So for example, 10 to the power 0 would be 1. 10 to the power negative 2 would then be 1 over 10 squared, which is 1 over 100. For the reflection questions, remember to copy these down and come to class prepared to discuss your answer to this question. Okay, so let's apply some properties of integer exponents, or basically develop them in the first place so that we can apply them. So remember that if I have 3 written as a factor 5 times, I can write this as shorthand 3 to the power 5. Right? Similarly, notice that if I put these 3's as factors in parentheses, this would be 3 to the power 4 times 3 to the power 1, which is just 3, written as a factor 1 time. Notice that I can combine these two powers here into 3 to the power 5. Similarly here, I can write this expression as 3 to the power 3. I can write this expression as 3 to the power 2. But notice all together I have 5 factors of 3, so I can write this as 3 to the 5. So all 3 of these expressions here I can write as 3 to the power 5. Notice that if I just take this piece here, 3 to the power 4 times 3 to the power 1, in order to get the exponent, I just basically add these the exponents here. So for example, let's say I'm looking to simplify 3 to the power 4 times 3 to the power 1. This would be 3 to the power 5 because 4 plus 1 is 5. Similarly here, if I wanted to evaluate 3 to the power 3 times 3 to the power 2, notice that that's just going to be 3 factors plus 2 factors, so altogether I have 5 factors. Okay, similarly here, I have 4 factors plus 1 more factor is 5 factors altogether. So what do you think would be, how would I complete this this expression here, or this equation rather here? Notice that this means that I have 2 factors of 5. This means I have 5 factors of 5. So altogether I should have 7 factors of 5. So this would be 5 to the power 7. In general, what we say is if you have any number raised to some power m times some other number raised to the power n, or maybe, the same number raised to the power n, you write that same number as the base and add the 2 exponents. For example, if I had 5 to the power 2 times 5 to the power 5, I would have 5 to the power 2 plus 5, which is 7. Let's see if we can notice a pattern when we're simplifying an expression like this. Well, if we expand out the numerator, 4 to the power 5, I have 4 written as a factor exactly 5 times. 1, 2, 3, 4, 5. Same thing with the denominator. I have 4 written as a factor 1, 2, 3 times. Notice that I can cancel these out, the common factors here, and I'm left with exactly 2 factors of 4, so I could write this as 4 squared. Notice that the result here, 4 squared, has the same exact base, as our original expression, just with an exponent here that's equal to the difference of these two. So I can take 5 minus 3 and get my exponent here too. You can use this pattern to simplify the expression, this expression here, since according to our pattern, right, 3 of these factors of 6 are going to cancel from the denominator and in the numerator. I'm going to be left over with 5 total factors in my numerator. So this would be 6 to the power 5. In general, what we say is if you have some number raised to the power m divided by the exact same number raised to the power n, this is just going to be that base a to the power m minus n. Okay, so take a look at this expression here. Notice that inside the parentheses I have 3 factors of 5. So that's what this is here. 3 factors of 5, and that whole thing is squared. So if you remember, if I have something squared, that means I take whatever's inside the parentheses multiplied by itself. Okay, so this would be 5 times 5 times 5 written as a factor twice. So here's what's inside the parentheses written as a factor once and twice. Notice altogether I have 6 factors of 5, so I could write this as 5 to the power 6. Notice that the pattern here is that the result, here's our result, has the exact same base. Here are the bases, with an exponent that's equal to the product, or when you multiply, 3 times 2, you get 6. You can also use this pattern to simplify this following expression. So this would be, what would it be? I would have 2 factors of 7 inside, but I have to multiply that by 4 because altogether I'd have 8 factors. So 7 to the power 2 with all of that raised to the power 4 would be 7 to the power 2 times 4, which is 8. In general, what we say is if you have some number raised to a power and that whole exponent, or the whole power, is raised to another power, then all I do is multiply the exponents together like this. Remember to write these reflection questions down, come up with an answer, and we'll discuss your answers in class. Okay, so let's say we have this big monster to simplify here. Okay, what the heck do we do? Well, you just take it one step at a time. The first thing you want to do always in math is follow the order of operations. So what comes first with the order of operations is the parentheses. So I take what's inside the parentheses. In this case, 5 minus 2 simplifies to 3. Here I have 5 plus 2 simplifies to 7. So I just simplified what's inside the parentheses. Remember, parentheses always comes first. Next, I use what I know about the properties of exponents to simplify this expression. So remember, the rule that we have says that if I have a product of 2 exponents like this with the same base, I just add the exponents. So this would be 3 to the power 5 plus negative 8 plus 7 to the power 0, but any number raised to the power 0 is just 1. So 5 plus negative 8 is negative 3, and I just simplified this. And then I'm going to use my properties of exponents to simplify this. 3 to the power negative 3 is the same thing as 1 over 3 to the power 3, and then of course plus 1. Adding these two things together, I get 28 over 27. So this entire expression here can be written simply as 28 over 27. I can do the same thing with this monster of an expression too. Follow the order of operations. First, simplify what's inside the parentheses. 10 minus 6 is 4. 10 plus 2 is 12. Next, I use my property of exponents. Once again, I have a product of 2 powers, so I add the exponents and simplify 12 squared, which is 144. 3 plus 2 is 5, so this is 4 to the power 5 plus 144. Just use a calculator to multiply 4 times 4 times 4 times 4 times 4. So 4 written as a factor 5 times is 1024, plus 144 is going to be 1168. So this entire expression can be written simply as 1168. Alright, so back to our question that we were trying to answer. How do you develop and use properties of integer exponents? Well, you can use the properties of integer exponents as a shorthand way of evaluating exponents and simplifying expressions using order of operations. Here are the 3 rules that we learned. First one is called the product rule. If you have a product of 2 powers with the same base, all you need to do is add the exponents. Here, the quotient rule. If you have one number divided by another number with the same base raised to different powers, you subtract the exponents. Similarly here, if you have some number raised to some power and that entire expression is raised to another power, this is going to be equal to the exact same base raised to the power m times n in this case. Alright, in your notebook, answer the following question. How can you use the expanded form to prove the properties of the integer exponents that we just showed? Give examples to justify your answer.